Okay, so we'll start the session now. So, welcome to week 12 of this Deep Learning for Computer Vision course. And in this week, we are mostly focusing on the very high level applications of deep learning. And so, for today's class, we'll revise some of these applications and go through their codes mainly. Right, so one such application is adversarial robustness. So all of these are potential research directions in computer vision, and yeah, I mean, if anybody is interested in any of these topics, they can just take them up, look at them, and pick up the very recent research problems that are prevailing in these areas. So for today's class, let me share my screen. Okay, so I do have some slides for today's class, but I was feeling like instead of going through the slides, we can go through the code base that we have, because that is really very informative, and you can learn parts of or maybe revise parts of the theory and go through the code parallelly. So but we'll start with some background. Okay, this just give me a second. Okay, somehow it's not going into the slideshow mode. Fine, I think we'll not go through this too deeply. Right, so yeah, so for week 12 we will be focusing on two such advanced topics. One is adversarial robustness, and the other one we'll come to shortly. So adversarial robustness is something that has been around for some the last 5-6 years, and there has been like a lot of research on this topic with thousands of papers existing in this area. So while sir has already gone through the topic, we will introduce it first once formally. What is adversarial robustness? Why is it required? And then we'll move on to the coding part, because there are the notebook that we have created is pretty dense, and yeah, I think it will be a much better exercise to follow than just looking at the slides. So yeah, so let's go into what is adversarial robustness. So while we all know that, we'll also see in the coding part that yeah, I mean, deep learning we know has made tremendous advancements in the recent years, but still there are some areas which need a little bit more attention. So yeah, just to recall, just to recap, this week we are, like in the classes also, we have seen that we are focusing on some of the advanced topics in deep learning, and today we will be touching upon two such topics, and the first one out of them is adversarial robustness. So one thing that we have seen is that like, even though our classification models are very strong and powerful, and we are able to generate images, neural networks can be fooled very easily, right? So, and there the deep learning world where we are still unable to do very well, right? So as and when these models are becoming parts of our lives, one thing that is seen is that there are attackers everywhere who are trying to take control of these models and basically do bad stuff with them. So one such okay, yeah, so one such area is called adversarial attack. So what you do here is that the models that we train, suppose we have a classification model, right? And the models that we train, so what are they exactly trained on? Do they see this image particularly? No. What they see is a grid of numbers. So for the models, this image means nothing. All it sees is a grid of numbers. So they are not humans like us. So the grid of numbers they try to find meaning out of them. Now it has been seen quite alarmingly that suppose I add a very small noise to it, right? So this is a random noise, and I am multiplying it with a very small value, right? So this product I am adding to the original image, and the final image that I see, as a human it looks extremely similar to me. I cannot find out any difference between these two. Yeah. Okay, where were we? Yeah. So I cannot find any difference between this image and this image, right? But to the in the eyes of the model or the computer, a lot of things have changed, right? Because all of they have divided this grid into maybe some 512 cross 512 numbers, and which is not perceivable to the humans, but that is how models recognize images. So what is the problem here? So it's already written in the slides. So suppose you have this image and the model is predicting panda with some confidence, which is okay high, and then you are adding a small random noise. Now it has given an image which is very similar to pandas. It's for us, we are perceiving it to be a panda only, but now see, the model's confidence has become 99.3% for a separate class called gibbon, which is not at all similar to the panda class. So this is what what the attacker wants to happen, right? So it is changing part of the image in such a way, it is creating small perturbations to the it is creating small perturbations to the image in such a way that the network is getting fooled completely, and the network is predicting the wrong things, right? And this in a sense can be very risky, right? Because if you are deploying a model for a certain purpose and your model is being fooled by just doing this sort of small perturbations, you can understand how difficult it is for the for the model users or the model creators to find out why the model is behaving so strangely. And the attacker, if he attacks the model completely goes haywire, and then bad things happen. So many risky things can happen, right? So this introductory slide kind of tells us what an adversarial attack is, right? And so let us start with the coding part, and maybe run maybe run a few codes and see what happens. So okay, yeah, so maybe we'll connect with the GPU, and we'll just go through this code, because this code has a lot of detail and this will be shared. So yeah, it is taking some time. Okay, so what we'll do in this particular piece of code is that we'll try to attack the MNIST, some pre-trained MNIST model, right? So we have this yeah, one second. Yeah, so we already have a Lenet model. Lenet, we all know about Lenet. So we already have a Lenet model that is trained on MNIST, right? So MNIST is again the data set of digits, right? So we already have trained the Lenet model on MNIST, and we are going to download that first using this wget command. So wget is a command which is followed by some downloadable link, and you can basically download whatever resource is there in that URL, right? So so now we have, with the by running this block of code, we have already downloaded the pre-trained Lenet model, and now let us look at what we are writing here, and many of this actually makes a lot of sense. So this tutorial, so let me do this. Yeah, so this tutorial will raise our awareness to the security vulnerabilities of the ML models, and what we are trying to what we'll do here is we'll use one of the first and most popular attack methods called the fast gradient sign attack to fool an MNIST classifier. So we'll basically see that MNIST being a MNIST contains what? It's basically a black background and some white pixels which denote the digits, right? So it's an extremely easy data set to predict, and even with a 2-layer neural network you will get more than 90% test accuracy for the MNIST data set. However, we are trying to show here that we will attack the MNIST data set in some way, and we will see that even with this simple data set which contains nothing but some zeros and ones in the pixels, the model is fooled to a great extent, right? So all of this, why is this research again required? Because even though ML is doing very well in the outside world, if you are not able to defend your model against such malicious people who are trying to attack it all the time, then you are basically you are basically putting yourself and all of the people around you under great threat, right. So let's look here what they have written in the threat model part. So there are many categories of adversarial attacks. So those will be covered in the class and by the other TAs. So there are many categories of adversarial attacks with different goal and assumption. So we'll basically this method of transforming the images or some model weights or whatever in order to for malicious intentions, those are called attacks as the action suggests, and the attacks can be of different forms. Two different forms explicitly, one is white box and one is black box. White box is what? White box attack assumes that the attacker has full knowledge and access to the model, including architecture, input, output and weights. So suppose if I am an attacker, this Lennet model that we downloaded here upwards, this if we are trying to attack it, basically we will be white box attackers. Why? Because we not only have access to the input data, we have access to the trained model, the output predictions, weights, everything. So we would be white box attackers. Now if we now move on to some black box attacks, black box attacks are a little bit more difficult because they assume that the attacker only has access to the inputs and outputs of the model and knows nothing about the underlying architecture or weights, right. So this would mean what? That it's more or less like an API access to the model, right. So it's as if we give the MNIST images as input and we get the class labels as output, nothing else is available with us. Now there are attack methods that can even like perturb the predictions. So what do you want? Basically you want the predictions to go wrong, right. So there are methods, black box attack methods, which do not even require access to the model, but instead maybe perturbs the input in such a way that the output predictions go wrong, right. So also in the eyes of the attacker, there can be multiple stages or multiple goals, right. So as bolded here, one is misclassification and one is source or target misclassification, right. So what is misclassification? Misclassification basically means that what you want as an attacker is that if suppose I have a digit 0, right. So your model should predict anything but 0, right. It can predict 1, it can predict 8, 9, anything is allowed, just that it should not predict 0, right. That is called misclassification. So all you want is for the model to misclassify the prediction, misclassify the output, right. And the other is source target misclassification. So this is more specific in the sense that suppose I have given image 0 as the input, and now I only want the predictions to be of class 8, right. So there is a specific source and target. So it means that the adversary wants to alter an image that is originally of a specific source class so that it is classified as a specific target class. So all of this has been already touched upon in the class, but we are still going to go through them because these are some notations and definitions that would be better to remember, right. So this is what we are, these are the different forms of attacks, white box and black box, and the specific goals that the attacker might have broadly include these two, misclassification and source or target misclassification. So the FGSM attack, which is the fast gradient sign attack, right. So what is it? It's a white box attack, right. White box means what? That the attacker needs access to not only the training data or the predictions, but the model architecture and the weights as well, right. So it's a white box attack with a goal of misclassification, meaning that if I have a image of a certain class, I am okay as an attacker if the prediction is just misclassified. It's okay to predict any other class, but it shouldn't predict the correct class. That's what I want, right. So now we'll move on to the attack part slowly, right. So the attack is called fast gradient sign attack, and it's actually a very simple attack. So all of these you will see that since this thing since this thing works, that given an image like this, I'll just perturb it by a little extent, and my the perturbed image will have a completely different like prediction. So since this thing works, so one thing has to be remembered, that any noise won't do it. So the noise that you perturb it with has to be chosen very carefully, so that your image is, so that your model is fooled, right. So since this very easy sort of a modification completely fools your model, so many people have come up with different ways of formulating this error part, right. And hence, so FGSM is just one of them, right. So it is one of the earliest and most popular adversarial attacks, right, and it is very powerful and very intuitive, right. So what is it? So let's go through this paragraph entirely, one sentence after another. So it is, this model is designed, this attack method is designed to attack neural networks by leveraging the way they learn, that is the gradients. So in a neural network, whenever we learn anything, starting from two layer hidden neural networks to GANs, the main way by which we learn is that there is a loss function that we always calculate, and then we back propagate gradients from that loss function, and then we update the weights by using the negative, by moving in the negative direction of the gradient, right. So the main thing that we always do is this negative direction of gradients, right. So we minimize the loss, and why? So when is the loss minimized the most? If we walk towards the negative direction of the gradient, that is what we will leverage here. So this negative direction of the gradient is the keyword here to be followed. Okay. So right. So the idea is very simple here, that again I am repeating this again and again, that normally our goal is just to minimize this loss by adjusting the weights based on the back propagated gradients. What the attacker does is that, like, it's a question to yourself, that can I perturb the input data in such a way that instead of, even though I am trying to minimize, as the model creator is trying to minimize the loss, but I have perturbed the data in such a way that it has, instead of minimizing, the loss is getting maximized based on the same back propagated gradients, right. So instead of a like minimization, maximization is happening, and that is happening because, how that is happening, we will go through that. But if suppose I am trying to minimize the loss, I am doing it by walking in the negative direction of the gradient, but if I try to do the opposite, I have to walk towards the towards the positive direction of the gradient. So that is what is leading me to maximizing the loss, right. So instead of gradient descent, if you can perturb the data in such a way that instead of gradient descent, you are effectively doing something like a gradient ascent, then you are done, right. Then in that case, what happens is, you are not able to predict the correct class at all, because you have basically maximized the loss for it, loss for that particular class. So basically what it says here, the attack uses the gradient of the loss with respect to the input data, then adjusts the input data to maximize the loss, right. So yeah. So now what they have done is, they have formulated with some notations, formulated the panda image that we are seeing here with some notations. What is the notation? So they are calling this image, the original image, as X, and the label is the ground truth class label is called as Y. And if we go back to the notations, we will see that there is a theta which represents the model parameters, and we know that j theta x comma y, that is generally the loss that is used to train the network. So this is here, this is here. Now the attack back propagates the gradient back to the input data to calculate this gradient, right. So what I will do is, I will take this loss function. Generally what we do, we calculate gradients with respect to all the weight matrices and weight vectors and bias vectors. Instead of that, in order to maximize the loss function, we will simply calculate this gradient with respect to the input image, right? Generally like we do in grad, like the visualization methods like GradCam and all. So we will calculate the gradient with respect to the input. Oops, yeah, we will calculate the gradient with respect to the input. Okay, now next step is what, that I need to change my training data, I need to perturb my training data in some way. So what it does is it adjusts the input data by a small step which is denoted as epsilon. So in this image that is given here, this 0.007 is the epsilon. So this epsilon is a weight by which you are multiplying your noise, the noise that you generate, right? So different people, like I said, they calculate this noise in different ways. So yeah, so this FGSM creates it in one way, which we will see. So this epsilon is set to be 0.007 in the picture. In the so what is the sentence then? Then that it adjusts the input data by a small step in the direction that will maximize the loss, right? So that direction is given by the positive gradient, right? So it will take the sign and keep that instead of like converting it into negative, right? So now it's a sine function, it will take only the signs, and instead of like converting it to negative, it will retain the whatever the original sign is, and this it will take, and this becomes the noise vector that we are seeing here, right? So this is given by the sign of the gradients with respect to the input of the loss function, right? The resulting perturbed image x dashed is then misclassified by the target network. Why? Because your loss function is calculated with respect to your correct class, right, which is the panda class. But now you have made sure that instead of that noise being minimized, you have maximized with respect to that. So in that case, the correct class in the eyes of the network will never be pandas again, right? Because for pandas you are getting a very bad prediction score, and you are getting good prediction score for other classes, and hence your model then misclassifies the image by some class like gibbon, right? Even though, so again the problem, the question here is that sorry for that, yeah. So it has misclassified the target network has misclassified the class as gibbon, even though in the eyes of the humans at least the image is clearly that of a panda, right? So now given this knowledge that we have of the attack, FGSM attack. So FGSM attack is then what? You have this original image, you will add an epsilon, and epsilon is this basically multiplied by the gradient of the loss with respect to this image, not the original gradients, just the sign of that gradient. And once you add that, that makes sure that you are not trying to minimize the loss, instead you are maximizing it, and when you are maximizing it, you are not moving towards the correct class, right? So that is how this simple attack performs, but it has been shown that with this simple formulation only, this attack has a lot like it can lead to very bad results, and it is very powerful. So let us run this. So some import functions that we have, right? So now in the so now that we are going into the implementation part, we will discuss the input parameters, okay, and define the model under attack. So this the next part that we will show, right? So that is that is not very important in this context, because it just defines the model architecture and maybe some data loaders, right? And here the main important, one of the most important things is this epsilon, right? So you can see here in this image that the epsilon is incredibly small, right? We will see what happens if we keep on varying the epsilon. So here with the small epsilon, so why is this small? Because you have to understand the challenge here, that if you have added something very small to the image, and as a human you are completely not understanding what changed. So this and this are very similar. right. So, we do not know what changed out of these two, between these two as humans, but in the eyes of the model, in the eyes of the computer, everything has changed. That is why the prediction has turned from panda to gibbon with an extremely high confidence. Okay, so this epsilon is a very is the most important input here, because that kind of defines the extent to which we want to perform this adversarial attack, right. And also what does 0 epsilon mean here? Epsilon equal to 0, that means that you are not adding any noise at all, right. So, you have that means what? That this image is basically the original image. So, what they are saying is that they want to retain the epsilon 0 in the list, because we want to show you what happens if you have the original image also in the test set, right. Because we need to compare the accuracies against the original data set only, that is why this is what we are doing, right. And also, like I said, that epsilon can be varied, right, and smaller the epsilon, the image is much closer to the original image, right. So, this is very small, that is why this is so close to this perceptually. So, now if you suppose, instead of keeping it small, if you are making it larger, as it says here, that larger the epsilon, the more noticeable the perturbations, but the more effective the attack, instead of degrading model accuracy, right. So, that is intuitive, because why? Suppose you have this small perturbation, right, that means your model, your image pixels have changed a little, but not that much. So, even though you know, it kind of reduces the accuracy to some extent, it is not a lot. But suppose if you keep on increasing the noise level, so you keep on increasing this epsilon, that means that the total noise that you are adding to the image is much higher, and hence the image starts looking distorted, but as a result, obviously the model accuracy also starts dropping a lot. So, that is what it is saying, that the larger the epsilon, the more noticeable the perturbations, but the more effective the attack. But the trade off there is that now if you have a human in the loop who is trying to like analyze why your model is having all these wrong predictions, it will be very simple for the humans to figure out that okay, the images are being perturbed, right. So, hence it is how to put it, hence all of these are kind of like trade offs, how much epsilon you want to put. So, you have to have a sweet spot where if you do not, if you, I mean the epsilon should be such that the image is not changed also to a great extent, but it is not very similar to the original image, then nothing works. So, now the data or the images that we are going to test with, so that is in the, that has already been normalized, it is in the range of 0 to 1, right. So, the epsilon value also should not exceed 1. So, if it exceeds 1, that would mean that the value here would go more than 1, which is something that we do not want, right. And we have a pre-trained model here, right, which is the Lennet model that we kind of downloaded above, and there is some other flag to use the CUDA, which is not important at all in our in this in whatever we are trying to do. So, we have already so okay, we are here, yeah. So, we have already kind of like defined that we want to do this for multiple epsilons, and these are the values that we will test the MNIST model with. So, it starts with 0, remember 0 denotes the what did I say, 0 denotes the case where I am taking the original image, then a small perturbation of 0.05, 0.1 and so on up till 0.3, and we will see how the accuracies change for all of this, and also how also how the image distortions change. And we have the pre-trained model stored here, so let us run this cell also, right. So, now basically small intro about this model. So, this is the Lennet model that they have defined for this okay, yeah. So, this is the Lennet model that they have defined for this purpose, which is a very familiar model with multiple conv layers and multiple FC layers. So this is not at all important for our case today. So this is just to define the model architecture, right? And also the test loader, which is loading the MNIST test set, right? So this is not, remember, this is not happening with the training set at all. This is not training. This is just that I am changing the image, test image in such a way such that my model is completely like making wrong predictions, right? So now so this part of this block of the code that you see, that is actually using the standard things like using CUDA and initializing the models, loading the pre-trained model, etc. Right, and you put it, like I said, this is not model training at all, that is why you put it in the eval mode, right. So all you need is a trained, you need a model architecture which is pre-trained on some data set, and you need the test data set for test data for that data set, right, and then you will see that what happens if you perturb the images, right. Okay, so we will run this one also. Yeah, so it's downloading all the test data, first of all the test labels and all, and then it is loading the model in CUDA, right. So we have initialized the model in this variable model. Okay, so now we already saw, we already defined while we were discussing that what is the perturbed image in FGSM. The perturbed image is image plus epsilon into the sign of the gradient of the image with respect to the loss. So this data grad, basically the one that is marked here, that is basically the delta x j theta xy, this one, right. So it is the gradient of the loss function with respect to the input, okay, and in mathematical terms it is x plus epsilon into sine of this gradient, right. So this is how this is the only formula that we'll use, so you can understand how simple this is. All these the above code you are pretty used to, because you have already trained MNIST and all. So all we are needing to do is we need to write a function which will convert our image to using this formula, right. And the only check that we have to maintain is that we want to like maintain the original normalized form of the images. So the to maintain that, the perturbed image is clipped to the range 0, 1, right. So now like we defined very simply, this is the attack code, nothing difficult to understand here. So there are three inputs to this, one is the image itself, one is the crucial epsilon value, and one is the data grad, right. So data grad is again the like the gradient with respect to the image, right. And now very simply we'll, instead of taking the data grad, we'll calculate the sign of data grad using data grad dot sign, right, and the rest is very simple. So we'll take the perturbed image and we'll initialize it using image plus epsilon times sign of data grad. This is exactly what we defined here in this region, and then the perturbed image is again clamped or clipped between 0, 1, and that is what we are doing using the torch.clamp function, right. Okay, so this is the attack model, attack code basically, and now we'll simply define how to use this attack on a test data, right. So instead of going through these words, I think the code itself is pretty elegant and easy to understand. So that is what we'll directly look at, right. So okay, so again like I said that there is no training involved here, it is only on the test side, right. So that is why the function itself is defined as test, okay. So and we are passing a model which was in the eval mode, if you remember, and this is the test loader and the epsilon, okay. So epsilon, let us get reminded once, yeah, these are the epsilons that we have, right. So if we are sending just one epsilon, we need to do it over a loop or something, okay. So this is only one epsilon it seems. So yeah, maybe we will repeat this for multiple times to cover all the epsilons, right. So this is so first we know the nature of these codes. So okay, let's do this. Yeah, we'll run this part. Yeah, okay. So what we are doing here is we are going through the test loader, looking at the images and the targets, right? So we are first sending the data to the CUDA device, right? And then the crucial thing is that for generally for the image itself, we do not need the gradients, right? So that is why the requires grad of the image is generally set to false, but here we are setting them to true. Because why? Because we need this quantity, this quantity, right? So because we need that, the gradient is set to true, right? And then you pass this image through the model and you obtain this output, which is which is the logit of the model, right? And this is the prediction, right? So this is so this is the init pred is the original prediction, right? And now let us go through this now. This is the more important part. So we have the loss function here between the output and the target, right? So they are using an NLL loss, which is fine, not our point of interest at this point. We are setting the model's gradients to be 0 to calculate the correct gradients, and now we are doing a loss dot backward. So this has back propagated the loss into the weight vectors for the weight vectors, and also because we switched on data dot requires grad, it will also calculate gradient with respect to data, right? And then now we collect the data gradient. So data underscore grad equal to data dot grad dot data, right? So this is how your you get hold of that gradient with respect to the data, and now you are calculating the perturbed data, and we are calling the FGSM attack function for that. We have the images, we have the epsilon, and we have the data grad, right? That will give us the perturbed data. Now to understand what is going on, now we have to send the perturbed data into the output, right? And then based on the output that we collect, we calculate a final prediction, right, with respect to the logits that we have, right? And then this part of the block, this code, basically what it does is it calculates the accuracy, right, with respect to the correct target, the ground truth target, and the final pred, where note that the final pred is basically coming from the perturbed images, not the correct images, right? So what they also have some blocks of code. So you can see that what they are doing here is that if epsilon equal to 0 means what, that this is the correct set of images, right? And this is a special case for saving. So they are basically saving the 0 epsilon example. So all of these are for right, okay, all of these are for for visualizations later. So they are doing it all for the cases where you are able to predict correctly, and also for the cases where you are predicting wrong. But this block of code, note that this has nothing to do with the FGSM attack or the model output or anything. So this is just some accuracy or some visualization sort of blocks of code, right? So this is calculating the accuracy and returning the accuracy, right? So we will run it quickly, right? It ran, okay. So now, like I said, that the last part is to run the entire thing, right? So now, like I said, that we needed some for loop for the epsilons to run it on all the epsilons, and this is what is happening, right? So for EPS in epsilons, we are just basically calling the test model, the test function again and again, and to the accuracies we are appending the accuracies. And for the examples, so this adversarial examples consists of, you can see that the adversarial examples that we are saving for the ground truth ones and for the incorrectly predicted ones, that we are noting down, okay. So although it's already done here, but we'll still let us run it by ourselves and take a look at what is going on. So it is what is it's printing the accuracies at for every epsilon. So it will be exciting to see like what is going on there, and based on the observations that we make here, it's taking some amount of time. We'll basically plot the accuracies, right. So you can see that at the epsilon 0, the test accuracy is 98.1%, right. Epsilon 0 means the case where your data has not been perturbed at all, right. And let us wait for a few more seconds for the model to return, the code to return the further accuracy values. Yeah, so you can see that it's coming up. Right. So now what we can, the pattern that we can see is that, yeah, the most clear thing is that it started with 98, then it reduced to 94, which is okay, fine. Then it reduced to 85, still okay. But then it reduced to 68, 43, right. So this is what is happening with the increase of epsilon. Okay, it's still running, but I think we have got the point that the epsilon, as the values increase, you can see that the accuracy values are reducing to quite an extent, and this is the last one. Yeah, at 0.3, which was our last value range, we are getting an accuracy of only 8.69%. We had started with 98, and with this epsilon we are getting an accuracy of 8.69%. So our model has completely failed now with this much epsilon. So first we'll here let's, so this is what the plot looks like, this is exactly what we saw. So the takeaway here is that with your increase in, by the way, yeah, let's look at, this is an epsilon versus accuracy plot. The epsilons, you can see they increase linearly, but the y axis is not linear at all, right. So it started somewhere like this, and then it suddenly started dropping, right, until it reached almost lesser than 10%, which is like lesser than random chance. For MNIST has 10 classes, so random chance is like 10%. So it became even lesser than that with a high the high epsilon value of 0.3. Now we wanted to like just to go through, we wanted to understand what this 0.3 epsilon value means at all, right, and that is what is given in this visualization. So I will just reduce the dimension a little bit here to like make sure that everything is in the screen. So this first row is for epsilon 0, then 0.05 and so on until this epsilon 0.3. So the first thing that we can see here is at 0.3 it's pretty visible that the images are distorted, right. So you are like making the model fail to a large extent, but at a high cost, right. So you are making the models the images visibly distorted, and then you are making the model fail. Similarly, the distortions can be seen here also, even though a little bit reduced than this. This is a little bit more reduced and so on. So we go on this one from here, it's very difficult. So when epsilon is 0.1, you can see that it's almost the distortions are to some extent visible, but not to a very large extent. And then this is the smallest perturbation that we have, and this almost has no visible distortion at all. right? So but still some all of these are misclassified samples, and so you can see that for some cases the model has added maybe, sorry, the attacker has added maybe some dots or something, right? So these have been added due to the perturbation in the image. So but this perturbation is enough to like tell the model that this is 4, right? So this is 8 is predicted as 0. So you even someone may come and say that maybe this 8, this 0 part, this upper round of 8 is more visible, that's why it can be predicted as 0. This 9, maybe if we distort the 9 part a little bit, it does look like 4, but this one is clearly 6, right? So this is not 7 at all. This is also clearly 7, this is not 2 at all, but still the model is making mistakes. And when the higher epsilon that you have, higher the epsilon, the distortions become more and more apparent. So you have to find a sweet spot where your model also starts degrading on the performance, but the perturbations are not visibly present. So this is the challenge that attackers have, right? And yeah, there are further links to look at here, right? So which you can have a look at on your own time. So this is mainly what we a good example of adversarial attacks, and since we are most used to with the the MNIST dataset, so we wanted to show you an example, a hands-on example on the MNIST dataset itself, and we showed some, we like this demo was on the fast gradient sign attack. So you can now understand like why, what is the application of this sort of a research area. So now how the research happens in this area is that first of all you need to like predict from beforehand or presume from beforehand that what kind of attackers can do from beforehand. So this is very similar to cryptography also, that you have to predict from beforehand that okay, the attackers can attack the model in this way, right? So that you have to predict first or foresee first, and then you have to come up with mechanisms to defend your model against those attacks, right? So papers come out in both these areas, and there are other multiple other areas as well, right? So like some of the, this is a very hot research topic, at least if not maybe in 2023, in 2020 around, it was like one of the hottest topics. It's still out there, so if anybody is interested they can have a look at maybe this topic in more details. There are multiple papers there on in every conference, including like high standard conferences like NeurIPS also, as mentioned here. So yeah, I mean this, all of these can be looked at in these conferences. So so in this, like we said, we began this class by saying that this week is entirely about the high level applications of deep learning, where deep learning models, deployable deep learning models are being used, or some of the, in other words you can also say what are the some of the real life deep learning problems, and this adversarial robustness is one such example. We'll also look at another example which is called pruning and model compression. So this deals with another so again this has been touched upon in class, but we'll still have a revision of this. So the concept here is again very similar in the sense that it's still trying to handle some real world problems that ML models face, but it has nothing to do with attacks, of course. The meaning of this or the purpose of this tutorial is something else completely, right? So you can see that this tutorial is borrowed from this particular person, but yeah, I mean again it's a very good tutorial and a good experience to go through in order to understand what is meant by pruning and model compression. So the moment we look at this title, right, the thing that comes, at least from model compression side, the what comes to our mind is that we are trying to compress the model in some way, and it is exactly that. The problem is that in deep world, in nowadays if you look at the current models, they are of billions of parameters and multiple billions of parameters, and such models, while they are very knowledgeable and they are very useful, they are not deployable in the real world, right? So many researchers have come up with many techniques to you know to handle these over parameterized models, and it has also been shown that, so one very crucial thing is that, as written here in the first two lines, that state of the art deep learning techniques, while they rely on over parameterized models that are hard to deploy, on the contrary, the biological neural networks that are in our brains, they are known to use efficient sparse connectivity, right? So this is, since all of this is kind of like inspired from our brains, we should also take inspiration from from the biology world. We should also take inspiration as to how efficiently the neurons connect with one another, and that too sparsely, not as thickly as our neural networks are, the artificial neural networks are, right? So the idea behind pruning is to compress these models by reducing the number of parameters, right, in some way. So in this tutorial is not really about what are those pruning techniques, because all of this we'll find in the in the class notes itself. So this is again a code walkthrough on how pruning can be used in real life, in an actual code, to investigate the differences in learning the dynamics between the over parameterized and under parameterized networks, right? So we have learnt all these methods, like role of lucky sparse subnetworks and initializations, lottery tickets, and so on. But the idea is that we'll now do it in terms of code, and we'll try to understand that how can we use these pruning techniques, whatever they are, whatever techniques we want to do, using PyTorch, right? So we, whatever we are learning in the class, we should be able to apply them in the real world if we want. If we have trained a very large dense model, and if we want to like sparsify them, then how do we do that in terms of code, right? So that is what we are trying to look into here, right? So in this tutorial we'll learn how to use the torch.nn.utils.prune to sparsify the neural network. So PyTorch has all sort of functions, and most of them we do not even know about. So pruning also comes as a tool in PyTorch, right? Okay, so we'll go through 90% of this code base, and 10% will be like homework. So once this is shared with you, so again, by homework I mean that this is for your own learning. We'll go through the general part of it, and the custom pruning, how you can do that, that is your exercise, which you will do if you find this interesting, right? So again, we'll try to run this code parallelly, so that we can, although all the outputs are available, but we can, it's still fun to run, right? So we'll start with, okay, so I think I'll have to leave this session. Okay, okay, if this is, anyway, so let's then not do this, it's causing errors. Okay, so again we'll move. So note that while we have the normal torch and from torch import nn etc., we have also incorporated this torch.nn.utils.prune. So from this module we are importing the prune function in order to prune the model, right? And we have, for comfort, we have defined the same Lennet architecture that we saw in the last tutorial, right? Okay, so this part again is not important for our main purpose of the class, so we'll maybe ignore it. And now suppose what we want is, we are trying to print the conv1 layer of the model, the parameters associated with the conv1 layer, right? And this is how they are doing it. So it's basically printing the weight, okay, all of these, and the bias, right? So this is the weight, right, and this is the bias. Okay, so this is what is stored in the pre-trained model in the conv1 layer, right? And we also have something called named buffers. We'll look into that later, what it is used for. For now we can see that this named module.named buffers is an empty list, okay, so nothing is there at this point. but something will come here which we'll look at in some time. Okay, so now pruning a module. So we'll start with how to prune maybe one of these, okay, the weight or the bias. So we'll start with the weight part. Okay, so what it says here is to prune a module, that is the Con1 layer of our LayNet architecture, first select a pruning technique among those available in the library, right? Or you can implement your own by subclassing the base pruning method. So so we all know that the codes that are the abstract methods that are available for in the library, they can be used and subclass to create our own personalized methods, right? Now what we have to do is, so in this step, the first step that we read through, we have selected a pruning technique, doesn't matter which one. Next step, we have to specify the module and the name of the parameter to prune within that module, right? So this we understand, so intuitive again, that what module do we want to prune. Here for example it is going to be Con1, and the name of the parameter, suppose the weight or the bias, right? Finally, using the adequate keyword arguments required by the selected pruning technique, specify the pruning parameters. So we'll look at what that means, right? In this example, most importantly, we will prune at random 30% of the connections in the parameter named weight in the Con1 layer. So like I said that for the beginning we will pick up the Con1 layer, and in the Con1 layer we will pick the weight, okay, weight parameter, and at random we are going to prune 30% of those connections, right? The module is passed as the first argument to the function. Name identifies the parameter within that module using its string identifier, and amount indicates either the percentage of connections to prune if it is a float between 0 and 1, right, or the absolute number of connections to prune, okay, if it is an integer, right? So instead of looking at all those theory words, this is the more like easy to understand. So we put prune, we had already imported prune before, if you remember. So going back, this is the piece of code that I am talking about. So we have already imported that, and now what we do is prune dot random underscore unstructured. So here these are all predefined functions in the library. So random dot unstructured does what? It just randomly prunes some connections. That what is sum, that is defined by you yourself as the user. So you have this module which we define to be the Con1 module, right? So module is nothing but this model.con1, right? And so this is module, name is weight. So instead of out of the weight and bias we are currently pruning the weight, and the amount is 0.3, right? 0.3. So we have mentioned here that we will do it for 30% of the connections, and that is why the amount is mentioned as 0.3, right? So now we have once we pass this through, once we run this cell, so then what we will do is, then a few things to remember, like pruning acts by removing weight from the parameters and replacing it with a new parameter called weight orange, okay? So now what has happened is that you are trying to prune some of the parameters, right, in the model, right? But it is important that you also retain the original values, right? And that is given by this weight orange, right? Weight orange stores the unpruned version of the tensor, and the bias was not pruned, so it will remain intact. So now if you do this, that printing of the module.named parameters, first you will get the bias which is given here. So all the bias values are printed. Next, instead of the weight, you will have weight orange, right? And you can see that, so this begins with 2.2429, 0.0080 and minus 0.0368. We will go up, and we will see whether it's matching, and yes, it's matching. So exactly the three values that we saw below, they are being retained, and you can go back on your own time to see that these two, the weight orange here and after pruning, and the weight before pruning, they are actually the same, right? Okay. So now how do you do the pruning? So you do that by generating a pruning mask, right? So the pruning mask generated by the pruning technique selected above is saved as a module buffer named weight mask. Okay, that is appending the underscore mask to the initial parameter name. Okay, and this is what this named buffers thing is becoming useful for. So initially we saw that this was an empty list, but now it consists of what is called the weight mask. Okay, so this is kind of like a mask of the same shape as the weight itself. 0 means that we are pruning this connection, 1 means that we are keeping this connection. So you can see that approximately 0.3 of the total weights are becoming kind of like zeros, others are remaining ones, right? So this weight mask tells you which connections to prune and which to keep in this weight vector, in this weight origin, right? Okay. Now for the forward pass to work without modification, the weight attribute needs to exist. The pruning techniques implemented in torch.nn.utils.prune compute the prune version of the weight by combining the mask with the original parameter. This is understandable, and store them in the attribute weight, right? So all you need to do is, if you do a module.weight, you will have all the pruned connections, right? So you can see that if you just look at these three, this row and this row, we see, or this first three, this first 3 cross 3 matrix maybe that I am marking. So the first one has gone 0, the third one has gone 0 here, the next row is completely 0, and the next row is completely 1. So we will see whether that is retained or not, and yes, so this has become 0, this is retained as 0.0080, this has again become 0, this entire row has become 0, right, and this is still retained because they were all ones in that position, right? So you can see that the code has worked and your parameter has been pruned, right? So yeah, so there are some details on pre-hooks and all which you can go and look at, but the more interesting case is now, so the above code is meant for the weights, right? And now we can also look at pruning the biases also, to see how the parameters, buffers, etc. Of the module change, right? And this time we are going to use a different pruning technique, right? What is happening here? We prune the 3 smallest entries in the bias by the L1 norm, and that is implemented in this function, L1 unstructured underscore unstructured, right? So again we will do the same thing, prune dot L1 unstructured, we will pass the module, name will be bias because now we are trying to prune the bias part, and amount is 3, right? So you can understand that this amount or whatever is here, this will change based on the pruning function that you are choosing, right? So once you run this, now again what will happen is the named parameters would now include both the weight origin, yeah, right. So we the named parameters will include both the weight origin from before, right? We had already stored that weight origin part, and the bias origin, right? So again everything is going according to plan because we had so our initially our biases were not changed, that's why we had retained the bias part. This time we have pruned it, so we will again for the bias the same things will happen. So we will have a weight origin here and we will have a bias origin here. And now the named buffers thing that was empty initially, and then it was filled with the weight mask part, it will now fill up with the bias mask part, right? We will see in the outputs that will be better. So you can see that when you do a module.named parameters, you are getting a weight origin and you are getting a bias origin here, right? So these module.named parameters, they will always retain the original value. So you can see none of them have turned into zeros or anything, all the original values are retained. Good. So now when I print the buffers, module.named buffers here, so initially if you remember it was the weight mask, but now it will consist of the bias mask as well, right? And you can see that since the biases are only 6 in number, you can see that out of these 6, So again this is different because we had made sure that in the bias one we are not pruning using the random one, we are pruning using the, we'll prune the smallest, three smallest L1 norms, right, three values with the smallest L1 norms. So we have pruned out these three. Okay, right, okay. And yeah, I mean let's verify also whether it has done the correct thing or not. So what are the three smallest L1 norms here? So you can see that this is there, this is there, and this is there, right. Incidentally these are also, if you sort them and then use the three smallest, these turn out to be the three smallest ones only. So anyway it doesn't matter. So this and this, so second, third and last should become 0, and exactly that has happened here. Second, third and last have become 0, right. So now like I told, like we gave the example that if we do a module dot weight, it will basically print your pruned weights. Here you do a module dot bias. So now you can see that the second, third and last positions have been made 0, the others are retained, right. So this is the main one of the main tools to prune this entire thing, right. And now we'll also so we did this entire thing manually, right. So we took a certain module and then we pruned them one by one. So now let's see what is meant by iterative pruning, right. The same parameter in a module can be pruned multiple times. So in effect, yeah, so in the initial stages what we did was we applied two different pruning techniques on the weights and biases. Now what it's trying to say here is that I can use another pruning technique on the weight itself compared to the previous one, right. So I can use a second pruning technique with the effect of the previous various pruning calls being equal to the combination of various masks applied in series, right. So now based on whatever techniques you use, if you have iterative pruning, like if you apply multiple pruning on a certain module, then the effect will be combined in the masks, in the masks that are getting generated. The combination of a new mask with the old mask is handled by the pruning containers compute mask method. However, I mean since these are already implemented for us, we do not need to worry too much about them, right. But let's see what they are trying to do here. So suppose that we want to further prune the module dot weight. This time using structured pruning, right. So this is another pruning. So along the 0th axis of the tensor, the 0th axis corresponds to the output channels of the convolutional layer and has dimensionality 6 for conv1, right. So based on the channels L2 norm. So we need not concentrate too much on the pruning methodologies at this point. The idea is just to show you in code, like if you want to apply another pruning method, how do you do that, right. So this is again like you can see that again you are defining module, the weight, some amount, right. There are some other parameters like n and dim. So right now as we can verify, this will zero out all the connections corresponding to 50% of the channels, right. So again, so this that is the function of this pruning function. So you can have a look at it, but but it's zeroing out 50% of the channels while preserving the action of the previous mask. So you can see this is gone, this is gone, this is gone, but whatever was 0 for the others, like this is a non-zero channel, but here it was made 0 by the previous pruning method and it is retained, right. So you have combined two pruning methods here that you are seeing by printing this module dot weight. Module dot weight will always contain the pruned values, right. Okay. Then there are other methodologies like serializing a pruned model. All relevant tensors, including the mask buffers and the original parameters used to compute the pruned tensors, are stored in the model state dict and can therefore be easily serialized and saved, right. So what this means is that if I just print the state dict, I'll find all the details. I have weight orange, I have bias orange, I have masks, weight mask, bias mask, right, and so on. So everything is, if I, so what is necessary for me to retain the original values and the masks, that's it, right. So I do not need to like retain the weight values also. All I have to do is I can take the original weights and the masks and multiply them, and that gives me my pruned values, right. So then next section is removing pruning reparameterization. To make the pruning permanent, remove the reparameterization in terms of weight orange and weight mask, and remove the forward pre-hook. So we can use the remove functionality. So once this remove functionality, that this means that we are trying to so we are again printing the named parameters, and we can see that all the values are retained. And now, yeah, these are all the masks. Okay. Okay, so there are some other interesting methods also here. So pruning multiple parameters in a model. So this is again something that I wanted to show you. So these parts maybe you can have a look at. They are not that interesting, but yeah. So there are other things like multiple parameters and global pruning. So global is down here. So we'll go through each of them because they are the more important and informative ones. So what is pruning multiple parameters in a model? So suppose what it means to say is that if I have, suppose a normal conv layer has what, a normal like convolution model contains what, it consists of conv layers, and it consists of FCs. Now suppose I want to like perform a pruning method on one of these, and some other pruning method on the other one. So suppose as given here, so we want to suppose prune 20% of connections in all 2D conv layers. So we'll have a if statement, that is if is instance module comma torch dot nn dot conv 2D, then prune dot L1 unstructured module comma name equal to weight and amount is 0.2. So we wanted to prune 20% of all connections in the 2D layers, in the 2D conv layers. That is what we are seeing. If it's the instance of this, then the amount is going to be 0.2. Now we want to prune 40% of connections in all linear layers, right. So that is what we will do. If is instance module torch dot nn dot linear this time instead of the conv, we will do the same. The amount will be 0.4, right. So you can again go back and see, like if we can like instead of using one like the same pruning technique here, can we change the pruning techniques? In my opinion, they can be changed. So yeah, I mean it's you can go back and have a go at it. Okay. Okay, so in global prune again, so like I said, the next important part is global pruning. Okay, so in global pruning, what we are trying to do is we only looked at what is usually referred to as local pruning, that is the practice of pruning tensors in a model one by comparing the statistics, weight, magnitude, activation gradient, etc. of each entry exclusively to the other entries in that tensor. However, a common and perhaps more powerful technique is to prune the model all at once by removing the lowest 20% of connections across the whole model. So what they mean by that here is that I have many layers. Until now I was showing that I went to a layer, I selected one layer, and then I selected one layer, right, and then out of in that layer I am going to prune 20% of the connections. Now I am saying that okay, I have an entire model and just remove the lowest 20% connections out of that, right? So this is what is written here, this part, the lowest 20% of connections across the whole model instead of removing the lowest 20% in each layer, right? So this will lead to what? This will lead to different pruning percentages per layer, but overall the uh, overall number of connections pruned is 20%. So this is the code for that, right? So you have taken all these parameters to prune. These are the parameters in Lenet, all the parameters, and all you need to do is call this prune.global unstructured, put these parameters to prune, and pruning method is like prune.l1 unstructured again, and amount is 0.2. So what this will do is that this will prune a total of 20% from the entire model, but maybe not all of each of these modules may not individually have 20%. So some of them may have more pruning, some of them may have less pruning. So these are this is again, this is global pruning. So this is also another technique that you can use, right? So next part is what I had told you about. So this is the part where you can use custom pruning functions. So if you want to write custom pruning methods, so all the some example codes are already given here, right? So you can maybe like have a look at them on your own, but a small summary would be something like this, that you you are a subclass of this pruning prune.base pruning method, right? And yeah, so now you are defining a pruning type unstructured, and then this is the mask that you want to generate. So this is how you can construct your own pruning function, by defining how to create the mask, right? So maybe you can go through this on your own. This is an exercise that that you want to do on which you can do by yourself. Okay, one thing I missed was this one. So this is the global pruning is what we went through, right? And yeah, so so global pruning is what we went through, and now after doing that global pruning, we can see something like this, that in individually in each of the layers we are only getting 5 to 8%, maybe in some layer we are getting 5%, 8%, 22% and so on connections pruned, but the global one is pretty close to 20. It's actually equal to 20, right? So this is what global pruning is about. So yeah, I mean this just maybe play with this piece of this code base. So this is very useful if you want to prune your model somewhere, and for researching obviously you have to know how to yeah, so for researching obviously you have to know how to write your own custom functions, but these are some of the primary methods to prune the different neurons of your model. Maybe individually you can do it, or you can do it for multiple layers for the entire model, or what we the other thing that we saw is that if some layers of your network are of a certain type, like all of them are con 2D layers, you can put one sort of pruning for them. If they are FC layers, you can use some other sort of pruning. Okay, fine. So so this is what I had for today, and yeah, I mean this entire week is about about making you interested in maybe some other some of the high level and highly researched deep learning topics. So I'm a little busy today, running a bit late today, so I'll call it a day. So hopefully you had a good time in this learning deep learning in this course. So yeah, we'll meet each other later sometimes, but yeah, all the best for your exams and the future endeavors. So yeah, I mean please play with these code bases that we are sharing, and also the slides that we are sharing and the ones that sir shared, so they are for your benefit. So yeah, so since I have a meeting now, I'll have to call it a day. So thanks a lot everyone.
Yeah, thank you so much.
Thank you.